Behold a visual testament to Axel Becke, a giant in the realm of computational chemistry whose work spanned from 1953 to 2025. This slide, titled The Architecture of Electronic Motion, frames his life's work as both a rigorous science and a structural art form. Through a sophisticated, blueprint-inspired diagram, we see the meticulous mapping of molecular geometry and electron density. By highlighting precise bond angles, from the tetrahedral 109.5 degrees to the linear 180.0 degree. The content celebrates Becke's enduring legacy in refining how we calculate the microscopic world. He didn't just study motion, he mapped the scaffolding of reality, providing the mathematical tools that allow us to simulate the invisible dance of electrons with unprecedented accuracy. Witness the staggering impact of a scientific titan. With over 110,000 career citations, Axel Becke ranks among the most cited researchers in history. His intellectual dominance is cemented by two landmark papers reaching number 8 and number 25 in Nature's all-time top 100. Today, his pioneering density functional theory, DFT, methods act as the invisible engines powering 80% of all modern quantum chemical computations. From the life-saving precision of pharmaceutical drug design to the rigorous demands of NASA materials science, Becke's legacy provides the foundational machinery for global discovery. He didn't just contribute to science, he provided the lens through which we now calculate the very nature of matter. Before he decoded the motion of electrons, Axel Becke was a tinkerer born in Germany and raised in Canada. Influenced by his father's precision as a glassblower, his early years were fueled by Meccano sets and a discarded chemistry textbook. Yet, Becke was no mere student, he was a true polymath. A fierce competitor, he conquered the Canadian accordion competition and set records in the long jump. This drive translated seamlessly into academia, where he earned a gold medal in engineering physics from Queen's University. Under Dr. Donald Sprung at McMaster, he laid the PhD foundation for a career that would bridge the gap between mechanical curiosity and the deep, orbital complexities of the quantum world. In the 1980s, chemistry reached a breaking point known as the fundamental crisis. While Walter Kohn had earlier revealed the Holy Grail, that electron density holds the key to a system's properties, the specific mathematical bridge remained a mystery. As we view this dilemma, we see a field divided. Wave function methods offered high accuracy but were computationally crippled by anything larger than 12 atoms. Conversely, early DFT, LDA, was fast but wildly inaccurate for chemical bonds. This slide captures a scientific world stuck between precise impossibility and efficient error. It was a landscape desperate for a new methodology that could marry speed with accuracy, setting the stage for a quantum revolution. In 1988, Axel Becke shattered the scientific status quo with the B88 breakthrough. He realized that earlier models suffered from a catastrophic flaw: they let the exchange potential vanish too quickly through exponential decay. This mathematical error effectively blinded researchers to the true nature of chemical bonds, rendering early theory useless for practical chemistry. Becke's solution, a gradient-dependent correction ensuring a proper -1 over our asymptotic decay, was the masterstroke the field required. Published in Physical Review A, this work ushered in the generalized gradient approximation (GGA) era. By finally allowing density functional theory to calculate molecular bond energies with pinpoint accuracy, Becke didn't just publish a paper, he authored the 25th most-cited scientific work in history, fundamentally recalibrating our digital lens on reality. Behold the resolution of a decades-long scientific trade-off. This comparative landscape, the evolution of electronic structure, illustrates how Becke's hybrid DFT harmonized two conflicting worlds. Before his intervention, researchers were forced to choose between the astronomical costs of accurate wave function methods or the rapid, yet wildly inaccurate, early DFT models. By introducing an optimized mixture for the treatment of exchange, Becke achieved the ultimate prize: chemical accuracy without computational bankruptcy. His hybrid approach bridged the gap between quantum chemists and solid-state physicists, transforming a niche tool into the universal standard of the 1990s and beyond. It remains the definitive best of both worlds, marrying high-level precision with the rapid efficiency required for modern discovery. Welcome to 1993, the year Axel Becke ignited the hybrid revolution. By masterfully applying the adiabatic connection formula, Becke discovered a Goldilocks solution to computational errors. He realized that by mixing a precise fraction of exact Hartree-Fock exchange with DFT correlation, the inherent flaws of both could be neutralized. The result was B3-LYP, a three-parameter hybrid functional that transformed theoretical chemistry. As shown in this mechanical visualization, the careful calibration of parameters 0.20, 0.72, and 0.81 yielded a tool of such immense utility that it became the 8th most cited scientific paper in history. This wasn't just a formula, it was the birth of the industry standard for chemical simulation, forever changing how we predict the behavior of matter. In 1991, the landscape of chemistry shifted not in a laboratory, but over a 5-course meal in Menton, France. This slide, The Cultural Tipping Point, chronicles the legendary Menton dinner where Axel Becke confronted the deep-seated hostility of wave-function purists. By successfully convincing John Pople to integrate B88 methods into the Gaussian software package, Becke transformed a decade of scientific skepticism into universal adoption. This pivotal moment triggered a global explosion in DFT usage, directly contributing to the 1998 Nobel Prize in Chemistry. It remains a testament to the power of intellectual diplomacy, marking the exact night a controversial theory began its journey toward becoming the bedrock of modern molecular simulation. Behold the 35-year climb toward total chemical accuracy. This slide, titled Climbing Jacob's Ladder, maps Axel Becke's systematic ascent through the hierarchy of density functional approximations. Starting at the base with LDA in the 1980s, we witness a relentless drive upward. Rung 2, the 1988 B88 functional fixing asymptotic decay. Rung 3, the integration of kinetic energy density in meta-GGA. Rung 4, the transformative 1993 B3-LYP revolution. Rung 5. The final pinnacle of double hybrids, 2022 to 2024. This ladder represents a lifelong perseverance. Each step refined the math, bringing the digital simulation of molecules closer to physical reality. Becke didn't just observe the summit, he built the staircase to reach it. Welcome to the structural heart of computational conflict, the impossible triangle of DFT. In the pursuit of functional design, researchers are historically trapped by three competing demands: simplicity, transferability, and accuracy. In this zero-sum game, satisfying one typically requires sacrificing another. While theoretical purists relied on exact constraints, often at the expense of chemical flexibility, Axel Becke pioneered a defiant semi-empirical approach. He chose to stretch the boundaries of this geometric prison by utilizing flexible expansions trained on high-quality experimental data. By prioritizing practical utility over rigid dogma, Becke provided working chemists with the robust, accurate tools needed for real-world discovery. He didn't just study the triangle, he forced it to expand. In the final chapters of his storied career, Axel Becke turned his attention to the most elusive of chemical ghosts, dispersion interactions. While standard DFT could map strong bonds, it remained blind to the faint van der Waals forces that dictate the stability of DNA and the folding of proteins. Collaborating with Aaron Johnson at Dalhousie, Becke engineered the exchange hole dipole moment (XDM) model. This was a masterstroke of late-career innovation. Rather than relying on empirical add-ons, XDM calculates these critical forces on the fly directly from electronic density. By mastering these subtle, non-local interactions, Becke bridged the gap between quantum physics and the complex, biological chemistry that sustains life itself. In the final movement of a legendary career, we witness Axel Becke reaching the theoretical summit between 2022 and 2024. With the publication of the DH23 and DH24 double hybrid functionals, he achieved a record-shattering accuracy of 1.76 kilocalories per mole, validated against a massive database of over 1,500 reference points. But the story doesn't end with mere numbers. In his final paper of May 2024, Beck performed an act of ultimate simplification. He collapsed complex dispersion damping models into a single, elegant parameter based purely on atomic numbers. It's a fitting finale for a man who spent decades navigating complexity, only to prove that peak performance is best reached through the beauty of simple principles. Step into the tangible reality of quantum chemistry, where abstract equations become the engine of discovery. This slide illuminates how Beck's B3LYP and XDM functionals have escaped the confines of theoretical physics to power the modern world. In the pharmaceutical sector, they act as microscopic architects, modeling the protein interactions vital for drug discovery. High above, NASA utilizes them to simulate the punishing thermodynamics of aerospace materials. From optimizing industrial catalysts in the petrochemical industry to refining electron transport in next-generation solar panels, Beck's work serves as the invisible scaffolding for global innovation. This is the ultimate legacy, a suite of mathematical tools that catalyze progress across every frontier of human endeavor. Step into the final architectural synthesis of a life's work. Here, we see the temple of DFT, built upon 4 unwavering pillars: Numal, B88, hybrids, and XDM. For 35 years, Axel Becke remained laser-focused on a single, titanic goal: solving the exchange correlation energy term within the Kohn-Sham equations. His core philosophy stands as a bold defiance against modern complexity. While others chased abstract virtual orbitals, Becke insisted that the heart and soul of reality could be captured using only the total electron density and occupied orbitals. It was a triumph of physical intuition over black box fitting, ensuring that his legacy remains as structurally sound as the pillars supporting this quantum temple. As our journey concludes, we look upon the full measure of a man whose existence was defined by constant motion. Axel Becke's legacy is more than a collection of prestigious honors, such as the Gerhard Herzberg Canada Gold Medal. It is a narrative of relentless persistence. This final slide captures the harmony between his towering intellectual achievements and his vibrant personal life. From the quiet serenity of the landscapes he loved to the competitive fire of his athletic pursuits, Becke embodied his own philosophy: science is not merely a destination, but a pace maintained over a lifetime. He leaves behind a world forever changed by his calculations and a family forever moved by his spirit. Axel Becke, a life lived at full stride.